So yeah, so what I'll do for the rest of the class is this. So till now, for any problem we faced, like let us say dark mismatch, or when the analog gain didn't match the digital gain, how did we decide to correct for it? Using digital calibration. So I'll try to give a brief picture as to how this digital calibration is done in practice. Okay, that's all, just for understanding. And for that I'll actually take this analog and digital gain mismatch as an example, because that is something we commonly do in pipeline ADCs. Because this capacitor mismatch, as I mentioned in the last class, if you are looking at 10 to 12 bits of resolution, by using an appropriate size you can get this. Only for higher resolutions you need digital calibration, but the gain mismatch will be there even at a reasonably low resolutions. So this is something that you need to worry about, and let's see how this is calibrated in practice. So let me take this. I'll actually copy this entire thing. Yeah, so I know that if the so the output of the pipeline ADC, as you know, we are reconstructing it like this: V1 plus V2 by G, that is the digital gain GD. And if the analog gain and the digital gain don't match, along with these two parts, we get this term, right? So let me rewrite it. So you have basically the desired signal plus the quantization noise from the previous stage that appears with this factor. Okay. So I'll also probably get rid of this to make space. So this is the final output. And I know that the first ADC can be modeled as the additive quantization noise. Fine. So now we know that if the analog gain GA and the digital gain GD are not equal, a fraction of this signal appears at the output. Right? In other words, if I were to find out how much my analog and the digital gains are matched or they are mismatched, all I have to do is this: I have to see how much of the signal added at this point appears at the output, right? But as of now, the only signal that is getting added at this point is quantization noise Q1, and you don't know anything about Q1, right? Because that is some signal that you have no information about. So as of now, since the only signal getting added is Q1, it is not trivial for me to see how much of Q1 is appearing at the output, right? So what do you think can be a solution for this? Basically, I want to find out how much is the analog and the digital gains are mismatched. And the proxy for that is this: any signal I am adding at this point, I know that will appear at the output if the gains are not equal. But as of now, the only signal that is getting added is an unknown signal Q1. That is why I am not able to directly go and find out how much of Q1 is added here, right? So if I were to get an information as to how much is the gain is mismatched, I should not be adding only an unknown signal.
You can add one more signal.
We need to add some known signal, right? Because anything added at this point will appear here. Fine. So we try to add a known signal, and that typically is what we call as a pseudo-random noise. So have you heard of pseudo-random noise before? Pseudo-random binary sequence?
Yes.
Okay. So this is basically we call it PN. This is basically a bit stream of ones and zeros. Okay. Something random. Okay. So it's a single bit digital bit stream. So it is basically mimicking a random noise, but it is not truly random because it is not trivial to generate a truly random signal. So that's why we call it pseudo-random, because this sequence you will find that it is periodic with some L samples, but the periodicity is quite long. So within that long period, if you look at the signal, it will look like a random white noise. So that's why we call it pseudo-random thing, and The nice thing is generating this is pretty trivial. You just need a bunch of flip-flops and an XOR gate and a few XOR gates, that's all. So that is why we prefer to use this. And since this is a random signal, if I look at its path spectral density, it will actually look flat like this. It will mimic a white noise like this. So if the path spectral density is flat, if I look at its autocorrelation function, how will it look like? Have you guys heard of autocorrelation before? So autocorrelation is the Fourier transform or the inverse Fourier transform of PSD. So if it's flat, the inverse transform is this. This just means that the signal is completely uncorrelated even if you shift it by one sample. Again, if you recollect, this is something we qualitatively understood when we looked at thermal noise. We saw that if a signal is not correlated with itself, or if it's not correlated with its next samples, the only possible sketch for the path spectral density is that it has to be flat. I'm just redoing the opposite thing. So which means the signal is only correlated to itself. Even if I shift the signal by one sample to the left or right, there is no relation. Okay. So now if I go and add a PN sequence here, how will the output change? If I add the sequence here, what will be the final output? Plus PN into? That is also going to come. So now my goal is this, right? I know that if the analog and digital gains are equal, neither of them will come. Now I know because there is mismatch, some portion of this sequence is appearing. Now my goal is to find how much of this sequence is present in this signal. And what operation do you typically do to find this? Maybe let us say I have two signals x1, x2. I want to find how much of x2 is present in x1. It is basically trying to find the relation between the two signals. So what do you do for that? I mean, it's all jargon, but you do the following: you take the signal, multiply it in time, and then you take the integration. Okay. That's basically called as correlation R. I mean, this shouldn't be surprising, right? See, what does Fourier series Fourier transform say? Any signal x of t comprises a bunch of complex exponentials like this. In Fourier series of Fourier transform, your job is to find how much of this fellow is present in signal x. So how do you do that? You multiply x of t and the other signal and you basically integrate, right? That's just finding the relation between two signals. You take the product of the two, we call it the inner product, and then kind of integrate, right? So same thing you have to do here, and this mathematically we write it as expectation of x1, x2, because loosely speaking expectation can be thought of as taking average. Basically this thing I am taking it like this, but the idea is this: you have to take the sequence V, multiply with Pn, multiply with the sequence you have added here, and take the average. That is the operation you have to do to find how much of this sequence is present in the final output. Fine. So let me actually copy this. Copy that. Copy. Yeah. So what I'll do, I'll actually multiply this by GD so that I don't have any denominator term. So then I'll have, so if I multiply this by GD, I have the first term having GD here.
Sir, Y is analog, right?
Y is analog, yes. Correct.
Can we add a digital thing?
At this point, I mean, as of now, you think about it, at this point it is analog or digital?
Has to be digital, right?
At this point it is digital, so you can add a digital sequence.
But Q1 is
Q1 is analog. I mean, the point is, see, this is the ADC, right? As of now, think of it like this. I'll come to the nitty-gritties later. Here it is an analog signal, now it's a digital signal. to the digital sequence I can add 1 or 0. Clear? We'll exactly see how we are adding it. That has some more details to be covered, but I'll come to that later.
Using the expression like it's y plus q2 is analog, then q1 is analog.
I mean, this is how we do it, right? I mean, you know that the digitization you represent it like this, isn't it? From here it is analog, here it is digital. But the way we model it is that some, error is getting added. Okay. So let me multiply this by GD. So I'll have this goes away. So here I'll have what will this change to? GD minus GA, and this will also become GD minus GA. And I need to basically do this, find the relation between the two signals by doing this GDV into V. Right? So which means I'll multiply this by the PN sequence. Each term, this is what you do, but internally what happens is this actually gets multiplied with each of these, and then you take the average of this. Now this is a completely random sequence, has no relation to the input. So ideally what will happen to this average? There is no relation between the two signals. Why will it get divided by 2? Think about it like this. Fourier transform, if some signal x of t has no frequency component, let us say you take Fourier series, right? I know that signal contains only these terms, right? So which means if I multiply with some other random 2 pi ft and take this, what will this be? The signal does not contain any term, so it will go to 0, right? That is what correlation or the relation is giving you, right? There is no relation between the two, so this will go to 0. Similarly, Q2 and PN are also have no relation. They have not seen each other in their life, so this will also go to 0. What about this third term? Again, this will also go to 0. What about the last term? Only that will remain, because the signal is correlated with itself. So only this term will remain. So ideally, this correlation will, let us say, tend to GD minus GA into some scaling factor. Let's not worry about, right?
So but PN itself is not correlated with itself.
Then if it's not correlated with itself, then what's the point? Why do you say PN is not correlated with itself? Yeah, you're completely understanding it wrong. Don't think from what you already know. Assume that you don't know anything. Think from scratch. There is a particular signal. Do you think it will be related to itself? That's all, right? That's what you are remembering things, but you are not remembering it correct. So that's why unlearn everything. Think from scratch, like with me, right? I am not assuming any prerequisites for this, right? A signal is related to itself.
Yes.
That's all. So if I take Pn and multiply it with this, right? So this will eventually tend to this ideally. So once I find the, let us say, this value, what can I find now? And which value is unknown here? The analog gain is what you don't know. From this you can find the analog gain, right? And once I find the analog gain, what should I do? I need to make the digital gain equal to the analog gain. So you change the digital gain to be equal to. So this is what, very broadly you have to do, correct? The idea is you try to get an estimate of what is the error, and let me delete this, that you actually do it by injecting a known PN sequence here. You find how much of this appears at the output by taking the relation between the two signals, this, and that gives you this value. From this you can find out what is the analog gain, and then you can go and change the digital gain. But in practice, we just don't do it in one shot like this. We try to do it in an iterative fashion so that even if there is any change, it gets tracked over time. And that's what we do, and the way we do is the following. So ideally, as of now, the correlation is this, right? Now what is the ideal value for this? If the gains are matched, what will this be equal to? 0. So what we do is the following. We try to find the error between the signals, that is the correlation value you get minus the ideal value you have. You take, let us say, the magnitude of the error and let us say define it as an error function or a cost function. You try to make sure that you choose the digital gain GD so that this error is reduced. That's what you ideally want to do. Fine. So if I actually go and sketch the error function or the cost function as a function of the digital gain. So let me simplify this. So this is basically what now? Tell me. Ideal value is 0. The actual value is this. So what is this equal to? Mod of GD minus GA. So I basically sketch these two. How will it look like? At GA, what will be the value? At GA, it's going to be 0. For greater values, it will do this. For smaller values, it's your mod function. Something like this. Now, of course, this is assuming that when you do the correlation, all of these will exactly go to 0, right? But in practice, nothing exactly ever goes to 0. It will be a small number. So if you probably try to get this plot, it will probably look like this, like a bell curve, right? So your job is to go and find the digital gain that makes sure that the error you have is as small as possible. You can't exactly make the error to go to 0. You try to make it as small as possible. Okay. And let us say now you start with, for example, let us say you start with one estimate of digital gain, right? Let us say your initial estimate of the digital gain is this. If you start from this point, to reach the ideal value of the digital gain, you have to move to the left or to the right? I should move to the left. Similarly, let us say if I started with an initial guess which is lying somewhere here. To reach the correct value, I should go to the right. Now, what can you tell me is different in this curve at these 2 points? The slope is different. At this point, the slope is positive or negative? If the slope is positive, to reach the ideal value, what should I do? I should reduce. At this point, slope is negative. The slope is negative. To reach the ideal value, I increase, right? So that is how we can iteratively change. So let us say at this point, I have an estimate of my digital gain, right? So to reach to the correct value, what should I first compute? I should first figure out what is the slope, right? Let us say find the slope dc by dgd. So if the slope is positive, I reduce. If the slope is negative, I increase. So you have to do whatever the slope is doing in the opposite way. And let us say some constant, typically we have something like this. And this is how you update your estimate of the digital gain, like this. Hold on. New. And this mu basically tells you how fast or how slow you can converge to the correct value. For example, if you choose a really small value for mu, let us say you start from this point, you will take baby steps like this, and you will take a long time for you to reach the final value. On the contrary, if you choose a large value for nu, let us say you start from here, you might reach close to the ideal value quickly, but you might be basically oscillating back and forth without ever reaching the exact value. So in practice, typically we start with a large value for this nu and then slowly reduce it. And this is not working. Yeah. And this technique is often called the gradient descent. Some of you probably have seen this. Right? And in practice, it turns out a better estimate is to not just look at the absolute error, look at the magnitude squared of the error. And basically if I take the magnitude square, it is simply GD minus GA the whole square, right? Nothing. And if you take this as your error function, then if I try to find the slope dc by dgd, push it down. If you take the slope, what will this be equal to? 2 times GD minus GA. And what is GD minus GA? It is basically the correlation value, right? So the slope is essentially 2 times this. So if you go and put that value here, this will be the current estimate of the digital gain minus mu into 2 times the, right? So let us say you call this to be mu by 2. So this 2 and 2 cancels. So you get with a nice clean equation, and this is what we call as least mean squares. Or we say it's LMS. So this is how we kind of do things iteratively. Instead of just finding the correlation value once and then finding out what is the analog gain and then making the analog gain equal to the digital gain, you do this in an iterative fashion, so that even if there is any change, it kind of tracks and makes sure that the digital gain reaches the analog. So yeah.
Do we do this like in the digital domain, or do we have the circuit that?
No, tell me, right? Should you be doing this in the digital or analog? What is this? I mean, we are correlating PN sequence with what output? I mean, which sequence? With V. V is an analog or a digital output. So you just have to do the correlation in digital domain. It's pretty trivial, right? Because V, we are multiplying with the PN sequence, which is 1 and 0. Multiplication is trivial. You just have to add it and then keep doing it. Suppose someone who has taken signal processing will understand this LMS, but even if you have not taken, you can actually understand it from a circuit's perspective. So that's what I'll try to do now. So let me take this equation. I'll do a reverse engineering. So this goes off. Remember, these are all discrete time sequences, right? So I can try to take the Z transform. If I take the Z transform of this, what will this be equal to? GD by R minus mu by Z minus 1. So I can write it like this: Z inverse by 1 minus Z inverse, which means I can say that GD of Z is minus mu into Z inverse by 1 minus Z inverse into, and what is Z inverse by 1 minus Z inverse? What operation is that? It's an integrator. Fine. So you can think of this entire business as following. Ideally, you want to make the correlation value equal to the ideal value of correlation. And what is the ideal value of the correlation? 0. Right? So let us say this is your reference value 0. What you do is the following. You have the computed correlation value R. You basically compare it with the ideal value. And what is the ideal value? 0. So at this point, what do you get? Minus R. So now you see that I have minus R. What is happening to minus R? That is getting integrated and scaled by mu. So I can draw it like this. It's an integrator. I'm just drawing a continuous time integrator just for simplicity. And then let's say it scales by mu. What will this give me? The digital gain GD. Once I have the digital gain GD, I can actually go and find the output as V1 plus V2 by GD. Right? Let me Now I have to close this loop. So what should I do next? I mean, how do you find R from this? You basically multiply the thing with, let us say, this is finding the correlation. You multiply with the PN sequence and average it. That will give you the correlation value. So what's happening in the background is essentially a beautiful negative feedback, right? And let us say this is a negative feedback system. So in steady state, what can you say about the signal here? 0, positive, negative. Why should it be 0? Why not positive? So yeah, so let us say we can contradict it if, let us say, I assume that the input is some positive constant. A constant positive value is given as the input to the integrator. Output will keep blowing up. If it's similarly negative, it will keep blowing down. So as long as I know that the loop is stable, this cannot happen. If the loop is stable, all voltages have to be finite. So the only possible solution is, I mean, this is same as your virtual ground principle, right? In your virtual ground with ideal op amps, we have something. So when do you say that this voltage is 0? Under what conditions is this voltage 0? If it's an ideal op amp, so what should be the gain of an ideal op amp? If you have an infinite gain, you can claim this. And if you have an integrator, at what frequency is its gain infinity? Integrator is 1 by S. Only at DC, you have infinite gain. So which means if I look at the DC here, that will also be 0. That's the same principle here also, right? The way you come to virtual ground is, you can assume that again the same thing. If the signal here is some positive voltage, a small positive voltage times infinite gain will be infinity. Similarly, if it's a negative thing, it will be minus infinity. If things are all working fine and things are all stable, then that cannot happen. So this has to be 0. Same thing is happening here, right? So if this goes to 0, which means the correlation value reaches the ideal value, which means in steady state, this will tend to your ideal analog gain. So this principle of using an integrator in negative feedback is one of the most powerful things you will find in all electrical engineering. You will find it hidden in so many places. Of course, it was hidden in this gradient descent LMS also, just that it was hiding in the background, you couldn't recognize. So you will find this in a lot of circuits also. And the principle is this: you want to have some quantity equal to some other quantity. Anytime you want something to be equal to some other reference value, you subtract the two, find an error signal, give that error signal as an input of an integrator, and then close the feedback loop. If you do that, the negative feedback and the integrator, they will enforce that the error signal here exactly goes to 0, and this will equal to your ideal value. So, I mean, without knowing anything, just from plain circuit, you can derive this LMS, and that is basically this. Right? Same idea, you want to make the correlation equal to 0, you put it, give it to an integrator, and do this. And then if you try to find an expression for the digital gain, that will basically give you this. Cool. So this is the thing we do. So now let me answer the question he asked earlier. So how are we going to add the PN sequence? So the initial answer I gave was you can add it here in the digital domain. So let us say you do that. Let me copy this. But the basic idea is this is what you do in practice. Now, how exactly you go and implement it, that gives you multiple variants. So let us say you add it in the digital domain. So to start with, let us say the ADC was a 2-bit ADC. So here you would have gotten 2 bits, 2-bit binary output. So what will be the number of bits you get here? You are adding 0 or 1, so we will basically have 3-bit now. So now the DAC has to be a 3-bit DAC. So that kind of makes the implementation a bit complex. So what is the other place you can add this PN sequence? Now I don't want to add it here. Oops. I don't want to add it at the output because that increases the number of bits I need. So where is the other place I can add? So that this point, remember this point should contain the input plus the quantization noise plus the PN sequence. That's all I want. If I cannot add here, where else can I add? We can try to add it at the input end. So erase this. So which means what you have to do is add the PN sequence at the input. But again, which means you have to convert this to an analog voltage. So if you have zeros and ones like this, you have to convert it to a voltage like 0 and some V0 and stuff, and then add it. But again, if you do that, what is the actual signal reaching the ADC? Y plus PN, right? So, and let us say if the PN sequence is 1, I am putting out a voltage V0. So the maximum I can have is, let us say, Y plus the voltage V0, and this has to be less than the full scale. That will basically restrict the maximum value you can have at the input. Right? You can no longer give a signal spanning VDD. It has to be smaller. So in practice, what we do is the following, or what is also done is the following. So I know that, erase all this. I know that, let us say I have a flash ADC, I have a characteristic like this. I know in a pipeline ADC, I'm not going to use the maximum gain here. I'll use, let us say, 1/2 the maximum gain or smaller than that. Which means, or why did we use a smaller gain to start with? What error exactly? Why did we decide to use a smaller gain here? If there is any error in these reference voltages, we are still okay. So now even if you make a small error in these reference voltages, because of the fact that I am not using the maximum gain, I am safe. So what you can also do is the following. If the PN sequence is 0, you shift the reference voltage to the left by small amount. If the PN sequence is 1, you shift it to the right by a small amount like this. Ideally, you want to compare Y minus Vref. Now what happens if the PN sequence is 0? You will be comparing with Y minus Vf minus some delta Vr. If it is 1, you compare with Y minus Vref plus some delta Vr, or vice versa. Whatever. Sign is probably incorrect, but you get the idea. So this is as though I am changing the input itself by so much. Right? So this is one way in which you can add without actually having to reduce the maximum signal swings you need to have here, or increase the resolution needed in the dark side. Of course, you don't change it so much, you keep it small. You change it slightly to the left or right by a small voltage so that you are still safe. So that is one thing. And another practical implementation issue with this is the following. I'll just mention it briefly, I will stop. Yeah. So here we are basically correlating with the final output. And I assume that all of them actually go to a very small value and you end up only with this term. But if you look at this, the quantization noise is a small value, it's a small signal compared to your input, and this is also multiplied by GD minus GA, so this is going to be really small, so this can go to 0 quickly, right? Similarly, quantization noise Q2, that is going to be small in amplitude, so even if you correlate with this and average it, this can also go to 0 or a very small value quickly. But if you look at this fellow, I have the input that spans the maximum range. So if you multiply with the PN sequence and if you try to take the average, if you want this to go to 0, you'll have to average it for a really long time, because loosely speaking this is containing maximum swings. If you want the averaged value to go to a very small value, you have to actually wait for a very long time. So that has practical issues, or sometimes this might not even go to a very small value. That is also possible. So this results in a long time for you to reach the optimal value. So to speed this up, what is sometimes done is this. Now the issue is the data with which I am correlating this PN sequence contains an input, right? Now the idea is to somehow eliminate this, and you can also think of different ways. One way I'll just mention and leave. So instead of having one ADC, you have two identical copies of the ADC. Let us say to this you feed one half the input, here you feed minus half of that input. Let us say these are D1, D2. So let us say you have first situation like this. How will you take the final output as? D1 minus D2? Fine. Now if I write the expressions for D1, D2, so D1 will contain the input plus ideally the last stage quantization noise divided by the digital gain, plus let us say the first stage quantization noise into the error. Fine. Similarly, if I write for D2, that will contain minus input plus some other quantization noise divided by some digital gain, and let us say plus Q2 into, plus quantization noise of the first ADC in that times this. Okay. Now my goal is to make sure that the sequence with which I am correlating the PN sequence does not contain the input. So can you construct a sequence from this that does not contain the input component at all? Yeah, you can let us say take D1 plus D2. If you take D1 plus D2, all I'll have is the quantization noise alone. So let us say this plus let us say Q1 into 1 minus GA by GD plus Q2 hat by GD hat plus Q1 hat into 1 minus GA hat by GD hat. Now remember I need to add two PN sequences. Let us say that is PN1 and PN2. Okay. If I do that, I'll have a portion of PN1 appearing at the output the same way as Q1, right? So you will have PN1 into 1 minus GA by GD. Similarly, the second sequence appears the same way as the quantization noise in the second ADC. So that will be PN2 into now let us say I correlate this with let me push it here. Let us say now I correlate this sequence with PN1, right? If I do that, ideally this term goes to 0, this goes to 0, this goes to 0, and this also goes to 0. And what will happen to this? If I correlate with PN1, you will get some non-zero value. This will be the only term remaining. And what about this? Because those two sequences have no relation, that will also go to 0. So this way you can actually avoid having to correlate with the input Y, right? So you correlate only with the quantization noise terms, and if you do with PN1 you get information about the first ADC. So using this you correct the gain in the first ADC. Now similarly, if I let us say go and correlate with PN2, all of them will go to 0, right? Now this will also go to 0 and it will only end up with this term. So you correlate this sequence with the second PN sequence, that will tell you the information about the mismatch in the analog and digital gains in this ADC. So you can go and tune the gain in this ADC. So this is one variant. Again, how we can think of whatever you want and do this. And this is just to give you some brief glimpse as to how things are done in practice, right? That's all. Cool. So yeah, that's about this. Yeah, before we leave, I'll just briefly mention this. See, now we have looked at pipeline ADCs and we saw things with flash. As I mentioned in the beginning, this whatever ADCs I have drawn here, they can be flash or a SAR. Okay, and in practice, the trend is to go and replace flash with SAR, and that's what is happening. And with respect to pipeline ADCs, there is actually a very good reason to do that, which is the following. So if you recollect, in a pipeline ADC, we need to do this. I have one ADC, I need to have a DAC and subtract this, right? And then you do amplify it and do this, right? Now if let us say use a SAR ADC. Now remember, SAR ADC itself is a negative feedback system. It has one comparator, and based on the output of the comparator you have a capacitive DAC that goes and feeds an appropriate reference voltage here. So now you see that the SAR ADC itself has a DAC, so you don't need to go and make a separate DAC. And also the important thing in pipeline ADC is to get this difference. In a SAR ADC, this point is directly giving you the difference. So you don't need to put extra circuitry to actually go and do this. The input of the comparator, after making minor modifications, you can directly get the signal. So now all you need to do is give it to a gain and then give it to a second ADC yourself. So this way the circuit implementation kind of becomes much more efficient and easier, and that's why pipelining is kind of almost done with only SAR nowadays. And this is commonly referred to as pipeline SAR.
For the SAR to actually give an output, it will take a lot of time.
I mean that you might think it's a long time, but the thing is it is all some logic gate delays, right? They can be made really small. It is just that it's a self time. So as long as the digital logic gates are sufficiently fast, which is now very easily to get in lower technology nodes, this is not a problem at all.
But still it will be slower than flash.
It will definitely be, it cannot be as fast as a flash, but flash has so many other issues that instead of doing that and tackling those problems, people are way off with doing SAR. Because the only thing in a SAR is the digital gate delays, and if you go to lower and lower technology nodes, digital folks have been making faster gates. So it is what it is. And again, if you actually look at the timeline, right, I always try to look at the timeline to see what caused what. So around 2005 to 6 is when we first came with asynchronous SAR. But SAR we knew for several centuries. There was nothing fantastic about it. And after this came is when things started, right? 2010 we had monotonic switching. Okay. And about 2015 is when the redundancy scheme we discussed came. And even this pipeline SAR came in the late 2010s. So again, just to highlight that, always don't think only in one domain. Don't keep your view only narrow. If you broaden your horizon and think from different things, it can actually lead to a lot of crazy things. I'll stop here. We'll meet after the break.